Let's look at a major complication that I swept under the carpet in the last video. If we look at the definition of the Lagrangian here, we've got the momentum coordinate for the Hamiltonian, the position coordinate, as it should be, and we've got the momentum and velocity, as it should be, to define the Lagrangian, except that these momenta are not related in the normal way to these velocities. These velocities were to do with the slopes of our paths, as you'd expect. It's the actual derivative of the coordinates xj in time. But these p's had nothing to do with the normal momentum. These were completely free variables, and we're in fact integrating over them from minus infinity to infinity, which is why our paths in phase space didn't have to bear any resemblance whatsoever to normal paths. One way of getting over the problem that these p's are actually just dummy variables they're integrated over is to actually perform that integral, in which case we'll just have functions of the paths themselves. The reason we've left that until now to do is that these integrands do not in fact decay down to zero as you go out to infinity. They do in fact increasingly oscillate as you go to large values of p because of the p squared and the Hamiltonian there, but that doesn't necessarily make them well behaved. You might suspect that for large values of p, because the integrand is oscillating so fast, you'll be getting positive and negative contributions next to each other, and so the integral actually won't be affected very much by those regions. And that's indeed true, but we still have this worry that we don't have the integrand going down to zero as you go out to infinity, and so you have this possibility of singular behavior. And in fact, we know that there should be singular behavior. The propagator here, the function we're trying to get, takes our wave function from one time to wave function another time. So when those times are equal, this propagator must in fact be the delta function. And delta function is a completely singular function, and so it's no surprise, in fact, that this is going to behave rather intensely in some limits. And in fact, that's really a feature rather than a bug. But you try telling that to Mathematica. If you go back to this integral and you put in the p squared on 2m and the potential in here, and then you try and do one of those integrals in Mathematica, it will say it can only do it if one of these terms like h bar or delta t has some kind of imaginary component. And of course we know that's not true. On the other hand, we also know that Mathematica is only going to try and give us finite values for the integral. It's only going to give us answers in terms of actual functions rather than generalized functions, such as the delta function. And we in fact deal with this integral in a very similar way as we deal with generalized functions, in that we force it through some artificial process to be finite, and then we take the limit as we make that artificial adjustment to zero. The adjustment that we're going to make is we're going to make this time have a small imaginary component. So if we take the integral and we examine that and we say, if this thing is zero, then this does not have an answer. But if this is a small positive number, this epsilon is a small positive number, then I and minus I gives us 1, and we have a negative coefficient to our p squared. So in the large p limit, this integrand is going to zero extremely quickly, in fact, and this is finite. And in fact, if we plug this into Mathematica and we say that this is real and this is real and positive and this is real and this is real and positive, we get the following answer. And we can see that that's a nice finite number, but we can also see that in the limit that this gets very small, we still have a perfectly well-defined result, except when delta t is also 0. And that's exactly when we'd expect this to be a delta function, therefore this should in fact be quite singular in that limit. So that all makes sense. So we can do this integral now. If we replace delta t with delta t minus I epsilon, we can do all of these integrals. So let's go ahead. So we still have these x integrals left, and this is going to give us our path integral. We're going to have n lots of these, so each time we do an integral we're going to get one of these prefactors. And this b is just going to be, we've got a p squared on 2m, so it's going to be 1 on 2m, and we shouldn't forget this h bar. We're going to have this exponential for each one of these integrals. If we have a product of a large number of exponentials, that's the same as the exponential of the sum of those terms. And we still have the potential term, which doesn't depend on p, so it factors out and then comes back into our sum in the normal way. Our a is going to be this derivative term on h bar. And as we can see, this bit here, when we go to the limit of delta t going very small, we can see that this bit here is going to look a lot like the derivative again. Which we can see looks exactly like the original Lagrangian, where we're really talking about paths with particular points in x and their derivatives, and so this is the Lagrangian as you might expect. And all of this here is equivalent to the path integral. So this is our other definition of a path integral. This is us taking each position. So these purple paths here, this is a much more natural expression of that. So each physical path has a particular derivative and has a particular selection of points in x as we go through time, and we take the action of those paths. The action is the integral. We note here we've got the sum, and in the limit that we take delta t to 0, this sum is going to go to the integral. All of this is going to be some big normalization factor, so we'll just leave that as some large normalization factor yet to be discussed. And of course, the limit that we take epsilon to 0, it's exactly the action. Just to reiterate, we have two different definitions of paths here because we have two different definitions of the action. In this action, we're talking about the action where we've got the Hamiltonian action, where we have these p's explicitly. So we're allowed to have our paths vary completely wildly, and we're also allowed to have any momenta we like. So these p's are completely independent of the paths. And if we add all those up, then we get the action very directly. If we get rid of those p integrals by actually doing them, then we get out normalization constants, but we then have a more natural path that is exactly just following our lines and calculating the action by integrating this standard Lagrangian along those paths. If this definition of these two different paths confuses you in any way, just look at the previous line. This is exactly what we mean. This is exactly what we mean.